Alright class, this video is going to be a continuation of the structural oscillation script that we wrote for Grasshopper. The script is going to adapt the geometry that we're taking from this script and organize it in such a way that we can assemble these bricks in IRL, in real life, with a robotic arm down in our fabrication lab. So the script that you have should result from two curves that you have, an upper and a lower curve, that are already tied to the geometry inside of Rhino. The only adaptation to this script that we need to make in order to make it function is to convert everything into millimeters. The simplest way to do that is to create 4 multiplication components and put 25.4. There are 25.4 millimeters in an inch. Our original script was organized using inches as the units. So we need to multiply all of the units, the brick height, the brick length, the brick width, and the gap, which is a variable, by 25.4. So I put in 4 multiplication components and 25.4 as my multiplication. And then each of these multiplication components need to be swapped out in each of the respective locations inside of your script. So you can just pause the video now and go ahead and organize that. Since I've already done it, I'm just going to skip past that. So again, multiply times 25.4 and replace height, length, width, and gap with their values multiplied times 25.4. The number of rows are not in inches. Those are literally the number of rows in your script that does not need to be replaced. I would be conscientious of the number of rows and the size of the geometry that you have. You'll notice that once you multiply times 25.4, you're also going to need to select the curves in Rhino and scale them by approximately 25 units, so that the brick size works approximately for the size of the new bricks, the bricks that are 25.4 times the size of the original ones you had. So make sure you get both of those things situated before you proceed. You should get a file that's looking somewhat like mine here, with 4 or 5 bricks in each row and 6 or 8 rows. So down here towards the end, well, I should say before we really proceed, you need to install the CUCA PRC, which is the plugin for Grasshopper that provides us all of the necessary components for creating a robot simulation and a robot script. On the Canvas webpage for the class, you're going to see there are 3 files to download. One is the setup file that you need to run as an installer. One is a license file for that setup, and another one is a custom Grasshopper component that we're going to use because our robot has a digital output, which is a little bit beyond the scope of what we can set up using the traditional PRC components. And again, the CUCA PRC is written by a group out of Austria called Robots in Architecture. They have a really fantastic website if you have never looked through it. Lots of different examples. The architecture forum and member section has lots of good examples of how the components work, as well as different examples of what people have used it for. I highly encourage you to check it out, especially if you're, interested in the future. So once you get that installed, you'll need to restart everything between Rhino and Grasshopper, and you should see a new tab, the CUCA PRC v2 up here. The first thing that you'll want to do is put in a core component. And as with most things in Grasshopper as we're working, we kind of work from front to back, or from back to front, however you want to sort of see it. This core component is the thing that writes all the files and that runs the simulation for your script. So when we hit the PRC settings, it brings up a different dialog box here. Basically, as you're writing the script, once everything is set correct and this thing turns from yellow to gray, it's going to start saving a file, and it'll save it every time you change something different. So for us here, I've set it to save to my desktop, and it's going to save this CUCA PRC. You probably want to put your own name in here, or some kind of designation, structural oscillation, something like that. It's going to save an .src file. The .src file is the file type that we use to actually write files to our robot. So what you want to look for here, as well as to come into the advanced setting and go to the license. And if you double click, depending upon what version of Windows you're running, if you double click the license file, so you should have already at this point installed the actual exe or run the exe file for CUCA PRC. Now you should be able to actually come in here. If you double click the license file, sometimes it'll work and actually allow you, it'll automatically change these registration settings. But if it doesn't, you need to come here. So under the advanced settings, so I've hit the CUCA PRC inside of the command code component, or excuse me, the core component from PRC. You'll probably see a temporary license here from the original install. You can put our license, which is set up for all the students and all students at UNCC, into this component. Because I'm recording this, I'm not going to put every piece in here. But in essence, you can come in, hit the edit license, and swap in or copy and paste our license into this and change the name and date that it expires so that it matches what you see on the license file. If you're having trouble opening that, open it with Notepad or something like that so you can copy the text out and replace it here in this dialog. And then you can hit exit and you are ready to start working with the CUCA PRC. As I promised, you're gonna work backwards with this. So there's 5 inputs that come in here: a tool, a robot, the commands, which are literally all of the commands that we want to send it, and a simulation. So some of these are very easy. The first one is that our robot is a KR60 HA. So we are looking for KR60 HA. There it is, KR30/60 HA. And we can put that in as our robot. The tool is going to be a shunk gripper right there. And we can put that in as our tool component. These things you can kind of pull down to the side because they're never going to change. We're just sort of setting the defaults. And then you can put in a simulation, a simulation which is just going to be a slider that goes from 1 to 0. And as you scrub this slider, you're going to see the robot actually move back and forth. So if I put in just as a very quick kind of way of demonstrating what's going to happen here, if I put in a PTP component and take the planes that are coming out just before we make the boxes for our bricks, take these planes and put them in, and then take this command and put it into the commands component, you're going to see that a robot shows up in the command here, in the setup here. If I flatten the planes before they come in, you'll see that we just get a single robot. And of course the tool is a little bit sloppy, and I'm getting an error that it's going outside, the tool paths are going outside of what the robot's capable of doing. But nonetheless, it will run the simulation, and you should be able to scrub from 0 to 1 across and see the robot actually moving to each of those planes. And you can see that the planes are actually misaligned. They're facing the robot rather than being aligned with the bottom of the brick. So as I sort of scrub this back and forth, you can see that simulation. So very quickly already we're sort of working with this simulation and with the setup. You'll also see that it's already out here written a CUCA project.src file. As I promised, it writes these right away as soon as you get the component actually up and running. Okay, so we'll go ahead and delete that. Okay, so the next part of this is to convert the planes that we have so that they're working functionally the way that we want. And how we want to do that is to create a series of XY planes. So those planes are going to be parallel to the ground plane, much like how we imagine the gripper approaching each of the plane locations that we have. And then we're going to use a plane align component, align plane component. And what we want to do is put points at, we want to put an XY plane at each of the points that we have, and we want to use this VROT, which is the rotated version of each of our planes, as the direction for these new aligned planes, and then these XY component to show what we're to give us the planes that are aligned now with the ground plane. And you can see them here. If I turn the preview off on everything else, we have planes that are following our curves for each of the brick locations, but are parallel to the ground. And I'll show you that in contrast with these planes, which are facing the robot. Okay, so you need to make sure that you're getting the appropriate kind of plane. Now we're going to have to do that twice, right? So we got to do it once with the even surfaces, and then again with the odd surfaces. So I will take and copy paste these, and you'll remember that we had to dispatch planes and tangents here, so you have to make sure you're grabbing the right set of points to go into the XY component and the right tangents, which are coming out of this VROT here, the lower VROT, to create these planes. And again, with the robot now, we're not concerned with the actual boxes. You can leave these if you want to see what the bricks look like, but really what we're concerned with are getting these plane locations, which is the actual spots where the bricks are going to get stacked. And then the last thing is to weave these two sets of lists. So we want to get every other row working, one and then the other, up through the system. So I'm going to take this weave component, and again I'll put a PTP component in so that we can see a simulation of these new planes, hopefully oriented correctly. So I'll zoom out to see where the robot is. You may have to actually grab the curves and literally move them closer to the robot. You'll see that the entire script adjusts based on your location, and you can see the PTP sweeps that are going to each of the various locations. Obviously there's a lot of other parts to this, but this is just showing, okay, it's doing the first row. Oops, looks like we need to flatten. So it's showing all of the robots at once. If we flatten it, then it will should straighten things out. So what we want to see is that it does the first row, the second row, the third row, and then the fourth row. We're still getting some errors in terms of the axis movement. I'm just going to adjust the locations of these and see if we can get it working. So you should be able to get your curves moved to an appropriate location where the robot is actually able to reach, and you just want to move those around until you get it to be able to run through the simulation. The other thing to note is that the PRC core has actually turned gray. And you want to make sure also that you're getting that this weave component, once flattened, should take the first row from this one, then the second row from that one, or then the first row from this set of planes, then the second row from this set, then the second set from this set, and weave them together to create the list that will slowly move up in the fashion that you want to actually stack a set of bricks. So if you kind of pay attention here, you can see how the robot is slowly moving up through the wall as it assembles things. The other thing that's really cool about this is that we can, here in Rhino, quickly scale those curves and see a bigger wall that actually processes through, or come back to the beginning of our script and change the number of heights or the number of bricks in the set. Obviously at some point we're going to go too high here, higher than the robot could actually reach, and or higher than a wall that we can do, but you can see that the simulation continues to update each time, and that the SRC file that it's writing to the desktop is actually also still working. So it's an entirely adaptive setup that we can accommodate to a lot of different wall types, or to a larger wall system. I'm going to switch this back down so that we're just working with 8 rows again, and with my smaller curves. There's no point in torturing the system, especially if your computer is working hard as you go. So I'm going to get rid of this PTP. Well, I can leave this PTP component in for now, and we'll start assembling other components to go with it here. Okay, so the next component of this that's important is what's called the command weaver. And this command weaver is, again, a PRC component, and this is what's actually going to stitch all of the various pieces, including gripper open and gripper close, together into the geometry that we need, or excuse me, into the commands that we need. If you zoom in on this command weaver, you'll see that there are little tiny plus symbols here that you can do to add more components. And basically what this does is same as the weave component here, It's going to allow us to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then return and take the second item from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and the third item, and so on all the way through until it's completed the task of stacking the bricks by going first to the conveyor belt and picking up a brick and then moving it over here to the locations that it actually serves. So what we want to start with are some of the locations that we set based on the actual location of the conveyor in our particular cell. What I've got here is I went ahead and set up two axis components. So if you just type in, double click and type in axis, we're going to do an axis movement, and that's what you're seeing here. All I've done is take and predefine each of the different components here, and I'm just going to pull them out so that you can see the values that are inside of each of them all the way through. And there are basically two different locations that we need to define. As we talked about last week, right above the location, we have one that's called above conveyor here, that's actually set to, so you're going to plug these into 1, 2, 3, 4, 5, 6 respectively. So make sure you pay attention to the order and then set the sliders to be the appropriate value. This one is 10 inches above the bricks at our conveyor, and this one is actually right at the brick, the location where the gripper will close onto the brick itself. So those are the first two pieces that we're going to start with, and we're just going to kind of go down the line of the 10 different components that we've got here. If you double click one of these or right click on one of these, you can change the name, and that's what I did here with above conveyor and at conveyor, just so that you keep track of what's going on. The next component, as we talked about last time, is that before the gripper closes, we need to put in a wait component, and it's just literally called CUCA PRC wait. We're going to put in the value of 3 for 3 seconds that it's going to wait while the gripper closes, and then that will eventually go into our command weave component. And then the next thing that we need is the custom component, the digital out signal, which is going to trigger the solenoid to close the gripper or open the gripper. And again, there are two commands that go with that. This is where you're going to want to use the KRC command component that you downloaded from Canvas. This is the third of the files that we're downloading from Canvas. And the simplest way to do this, I think, is just to drag that file right into your Grasshopper component. And you can see that this is just a custom cluster. It's looking for an IO, which is literally the location for the digital signal for the gripper to open or close, and the state, which is going to be a true or false component. And that's going to output the command that the robot is looking for. So what we want to do actually is set a couple of state versions for each of the components that we have. So I'm going to start off by making 2 of these and then put an 8 in and a 9, and the 8 signal tells the robot to close the gripper, so I'm going to right click on this and change this to close gripper, and the 9 signal tells it to open gripper, and I'll put the 9 into the IO for this one. Then we can put a Boolean toggle in, which is just a true-false toggle, and I'll leave it on false and make a copy and put this one here. So basically all we're doing here at the beginning of the script, and again, you can imagine that we're just going to work our way right down this list to keep things very organized and very deliberate. So you want to be really smart about how you organize these. If you want, you can select and then hit these 2 little boxes and it'll organize things so that they're very square and direct. These 2 components then are, by setting them to false, are making sure that the gripper is open and that it's ready for business. So neither gripper closed or gripper open is set to anything, then the gripper should be open and ready to go. So, and then I'm going to copy these 2 pieces. And what we want to do now is, after this wait component, we've gotten to the location of the bricks on the conveyor. Here's the wait component that's going to tell the robot to wait there for 3 seconds while the gripper closes. So I'm going to switch this to true, the gripper closed to true, and this gripper open we're going to need a little later, so I'm going to pull it down. So now the gripper is closed. We've waited there for 3 seconds. The next move is to move to a location approximating where our brick is actually going to get deposited. So where this is about 10 inches above the actual location where the brick is going to go. So we need to take this set of planes, this woven set of planes that we've put together from our structural oscillation script, and we're just going to put a move component on it and take these out. That's what goes in the geometry. We're going to move them in the Z direction, and we're going to move them not 10 inches but instead 254 millimeters, which is the equivalent of 10 inches in millimeters. So these moved planes now are above our actual planes where the bricks are going to go. We're going to use a PTP move to move to each of these locations once we've got the brick. And then we're going to want to actually do a linear move, so straight down, linear movement, and that's going to go to the actual locations of the bricks. So we don't need this PTP any longer. So the PTP move, again here, is the one that's 10 inches above, or 254 millimeters above the original location. The linear move then is going to the actual locations of the bricks. So this is first, this is second. When we get to that location, we need another wait command. So we can select these two components, hit copy paste, and then lastly open the gripper. And that'll deposit the brick where it needs to be. Then one more move is a linear move, this time back up to the components which are 10 inches above our original location. And that move there is actually reminding me that once we close the gripper, we need one more component in here, which is a linear move back up to this above conveyor. What I'm going to do is just leave this here, leave a gap so that I remember, and I'm just going to put a panel in here to remember that we want to move back up linear before we actually start making the moves towards the wall itself, towards the wall assembly. So once we've closed the gripper, once we've closed the gripper on our component here, we're gonna move back up off of the conveyor itself, and then start moving to the locations 10 inches above the bricks to the actual location where the brick is. Wait for 3 seconds, open the gripper, and then make a linear move back up before then returning to the top, which moves to this location 10 inches above the conveyor. So that should be everything we need in order to start putting this together. The last part of this is to make sure that our lists are all exactly the same length. That's to say that when we weave through the command, that when this command weave goes through, that it has the exact number of open grippers, closed grippers, above conveyor, below conveyor, different pieces that we need in order to ensure that that the component works. So what we need to do in order to generate that is to put in a duplicate data component right here. And that duplicate data component is going to be driven by the number of bricks that we have. And that we can find here under these PTP moves. So I'm going to get a list length. It's just going to tell me how many, literally how many planes there are. When I mouse over it, you can see there are 29 bricks in our assembly. That looks about right. This list length is going to tell us how many times we need to duplicate our data. So each of these duplicates is going to be driven by this same length component. And I'm going to come along and copy this duplicate component all the way along here. Only swapping out the data that comes out, not swapping out the length. So the length is going to drive all of these. So I'll do copy paste. This is above conveyor, at conveyor, the weight, close gripper, now when we get here, these PTP moves and linear moves already have 29 surfaces in them. They don't need to be duplicated. So we can skip past each of those, duplicate the weight. We could also use the same weight component up there again, duplicate the open gripper. I'm realizing too that we're going to need not just to open the gripper, but also to turn the close gripper back to false. So here I'm going to put in, I'm going to put in another little note reminder saying close gripper false. And I need to hit this one back over to true. So this open gripper should be true, as in open the gripper, and this closed gripper needs to get turned to false. We already have one of those. It's up here. I'm just going to use that one again when we get along. So what you can see is any of the given components that are driven by our planes, or are the locations of each of our bricks, are going to are not going to get duplicated. And all of the command components that just have an individual object in them are going to need this duplicate component, so that we have the exact number of pieces that we need all the way along. So this sim slider can go off. Now what we're going to do is just literally drop these into the weave right in order as we go down the list. So first one is the close gripper false, then open gripper false, then above conveyor, then at conveyor, then the weight, and then the close gripper to pick it up, then 10 inches, move back linear. So now we need to go back up above. So I'm going to put this one in again. That's going to move back up above the conveyor. And then these PTP components, which is up 10 inches above our planes. That's from the moved version of our brick locations. Then a linear move down to the actual brick location. Then a weight, and again, make sure you're coming out of the duplicate. It looks like we're going to need a couple of more here, so I can hit that little plus signs again. Now, close gripper false. That is back up here. That's telling it to open. It's the first part of opening the gripper. And then open gripper true, which is set to true right here. Put that into 12. And then one last one, hit a plus again for a total of 13, is a linear move back up away from the wall before then returning to the top, where it will open everything, make sure everything's set to false, and then go to the location above the conveyor. So kind of complex once it feeds into the command weave. The command weave all comes in here. But what we can do now is back out, and with the simulation slider, start to see that the robot is going to this location, which is over here, is relatively close to, this is the conveyor location. You can see how it's always returning to that spot. And then moving to each of the given brick locations. So now what we know is that the location of the end of the conveyor is over here. So we're going to need to move our curves somewhere over here onto the table surface that is in the space. So you can tell from the given locations where the conveyor is where the table is, and that's where you're going to want to locate your curves. So if you might remember, and this is interesting, you start to see when I get to a given side that the robot infers that PTP move over to the right sometimes, and then over to the left in other instances. It also appears that I have got some moves that just aren't working. I might be too close to the robot. Rotate these guys a little. You have to kind of adjust them. Just going to keep checking this. Contain unreachable positions. So we're going to keep adjusting the brick, the curve locations here until we get things to work. So you should see in red the locations where it's not working. Not quite able to tell why the reach isn't working. It seems as though it should be. It's actually doing everything that we want to in the organization here. So I think we've got it right. It's just giving us an error. At this point, we can go try the script to see what we get. So you can see here it comes to a home location to start and to end. It goes to the end of the end of the conveyor to actually create the moves up and down, and then moves over here to our brick locations and is dropping 10 inches linearly as it comes. So it's a really great visualization of what's actually happening with the script that we wrote. Lastly, you can just kind of confirm here. If you go to settings, I'm just going to put the number 1 at the end of that and hit exit, and then out here I should have a new file. I'm not seeing it. I think it might not be writing it because it's still red. Or I'll hit apply and then hit exit, and let's see if that wrote it. Yes, so here we've got our CUCA project .src. So you'll want to upload this along with your Grasshopper script when you get everything done and working for this your first robotic program. Congratulations.